Hi everyone, I'm Julia, the chemistry tutor. Welcome to my website. Today I am going to talk about stoichiometry. Okay, it's the math that you are going to do with all of your chemistry from here on out. Like when you start learning stoichiometry, you are going to use this for the rest of every chemistry class that you take. This is the most important math of chemistry. Okay, so don't stress about stoichiometry. Stoich means elements. Metry means to measure. We are just measuring elements, okay? We're just measuring stuff. All right, so let's get started. Okay, I'm going to start off talking about moles, okay? Because moles is the thing, it's your hub. It's where you're going to go to. If you don't know where else to go, you always go to moles because everything takes you to moles. Okay, so first let's talk about what a mole is. Okay, so we either call it MOL or MOLE. Okay, mole. And what it is it's how we measure chemicals. Okay, it's a mole is just a batch of chemicals. Chemicals are so small. Okay, your molecules, your atoms, your elements, they are so small that we can't actually see one at a time. So we look at them as batches of things, okay? So it's like if you are going to the grocery store and you're going to buy eggs, you're not buying eggs one egg at a time. You buy eggs by the dozen or 2 dozen or dozen and a half, or right by the case, which is I think 3 dozen, 12 dozen. So you buy your eggs by the dozen, not by individual eggs, because an individual egg doesn't really do you much good. So it's the same thing when we're talking about chemicals, okay? We don't look at chemicals by one molecule or one atom at a time. We look at them in batches because one doesn't really do us much good. When we have chemicals, we have them in major amounts, okay? So the mole is the batch that we use for chemicals, whereas like the dozen is the batch that we use for eggs. Okay, so let's take a look at this. So if I had 1 dozen sulfuric acid, H2SO4, okay, so if I had 1 dozen of those, I would have 2 dozen hydrogens, right? Because a dozen and 2 hydrogens each one, if I have a dozen of those, I have 2 dozen hydrogens. I have 1 dozen sulfurs. Okay, one of those I would have 1 sulfur. 1 dozen of those I would have 1 dozen sulfurs. Okay, I would have 4 dozen oxygens. Because if 1 dozen has four, if one of them has four, 1 dozen has 4 dozen. Okay, so I hope that makes sense. So now we're just going to say mole. In 1 mole of sulfuric acid, I have 2 moles of hydrogen. I have 1 mole of sulfur. I have 4 moles of oxygen. Okay, so we're just saying a mole because we might have said in 1 molecule of this, okay, we would have 1 atom. Oh, sorry, 2 atoms. 2 atoms of hydrogen. 1 atom of sulfur, and 4 atoms of oxygen. Okay, now we're just saying moles. Okay, and a mole of sulfuric acid, 2 moles of hydrogen, 1 mole of sulfur, 4 moles of oxygen. Okay, so that's our moles. That's what a mole is it's just a batch. It's just an amount of stuff, okay, an amount of chemicals. Okay, and the reason that we do that is because they're so small that we have to look at them in batches, and the batch that we use is a mole. Okay, so now we understand that a mole is just a batch of stuff. It's just a number of things, like a dozen is 12 things. It's just a batch of stuff. Okay, so just like with a dozen, it can be a dozen anything. It doesn't matter what you're talking about. A dozen cars is 12 cars. A dozen, I don't know, trees is 12 trees. A dozen anything is 12. So same with a mole. Okay, a mole has a certain number associated with it. And 1 mole is, and I'm just going to write it as a conversion factor, is 6.022 times 10 to the 23rd. And these are, we're talking about things, right? So like with a dozen, we're talking about things. We're talking about eggs, chairs, whatever. With moles, we're talking about chemicals. We're talking about moles of sodium chloride, moles of copper, moles of carbon, moles of whatever. So 1 mole of whatever you're talking about is 6.022 times 10 to the 23rd of those things you're talking about. And some instructors use 6.02 times 10 to the 23rd. It just depends on your instructor. That fourth sig fig might change your answer a tiny bit, but not typically. So whatever it is your instructor uses, whether it's 3 sig figs or 4 sig figs, use whatever number they use. Okay, so just like that is the concept of just like 1 dozen things, whatever we're talking about, is 12 of those things. Okay, so it's just a number of things. It's just a batch of things. Okay, but let's visualize how big that number is. Okay, 6.022 times 10 to the 23rd. If you had that many soccer balls, okay, if you had soccer balls, 1 mole of soccer balls is 3, oh, not 2, 3 times the volume of the earth. Okay, so you could not fit a mole of soccer balls on the planet Earth. It would not be possible because it's 3 times that big. That is how huge that number is. A mole of M&Ms would fill the oceans completely and then be like a foot on all of the planet Earth after having filled all of the oceans. Okay, so, and that's M&Ms. So a mole is huge. That is a gigantic number. Okay, and like if I had 1 mole of water, that is approximately 18 milliliters of water, which is not very much water. Okay, because what is it? It's 283 milliliters, I think, is a cup. Okay, I might be wrong on that number. Don't quote me on that number. But maybe it's 238. I think it's less than 250. I think it's 238. Don't quote me on that. Okay. So 18 milliliters is a tiny, tiny volume of water. And that is a mole of water. That is 6.022 times 10 to the 23rd molecules of water. Okay, so that's why we look at elements, at chemicals, by the batch of a mole, a huge number. So it's actually enough there for us to visualize, to see, to physically be able to see it. Okay, so we just look at things in numbers of moles in chemistry. Okay, so I had just mentioned to you that 1 mole is 6.022 times 10 to the 23rd. Okay, that is Avogadro's number. Okay, that is a number that you are probably going to need to memorize because that is a conversion factor. Okay, it's just like if I said a dozen is 12, it's conversion factor. Okay, so that is Avogadro's number, and that is a number you are going to need to memorize. And you're going to use it for a while in chemistry, and then maybe if you take other chemistry classes later on, you would use it a lot more. Okay, but we use it for a little while now just to get us going on our conversion factors. Okay, so that is the number of things that are in a mole, and a mole is just a batch of stuff. Okay, so now we're going to talk about the mass of a mole. Okay, so the mass of 1 mole. Okay, so if you think about it, if I say the mass of 1 dozen, it depends on what we're talking about, right? Because 1 dozen chairs is going to have a very different mass than 1 dozen eggs, right? Even though they still have 12, no matter what, you still have 12 chairs in a dozen, 12 eggs in a dozen. They have a very different mass. Okay, so it's the same thing with moles of things. It depends on what you're talking about. Okay, if you were talking about like carbon, we always use grams, right? We're in the metric system when we're talking about chemistry. So if I were talking about grams of carbon in 1 mole of carbon, right? 6.02 times 10 to the 23rd atoms of carbon, so 1 mole of carbon. What would that 1 mole of carbon weigh? Well, we go to the periodic table for that information. Okay? And on the periodic table, your mass on the periodic table, we have been calling AMU. So far, we've been calling that atomic mass unit. Okay? Well, now we are going to call that molar mass, which is the mass of 1 mole. The mass of a mole, molar mass. So it's your number of grams. And if we look at your periodic table and you look up carbon, carbon says it weighs 12.01. That is 12.01 grams of carbon in 1 mole of carbon. Okay, if you went to the periodic table and you looked at sodium, and you see that it's 22.99. So I have 22.99 grams of sodium to 1 mole of sodium. Okay, it's still 1 mole of carbon is 6.022 times 10 to the 23rd atoms of carbon. Okay, 1 mole of sodium is 6.022 times 10 to the 23rd atoms of sodium. They still have the same number of atoms, but they have a very different mass. Okay, because they have different numbers of protons, different numbers of neutrons, and that is your mass of an atom. So if they have different numbers of those, then they're going to have a different mass. Okay, so just like my chairs and eggs would have different masses, even though they each have 12 things, they have a different mass. Okay, so we've talked about molar mass, which is your number of grams in 1 mole, and we've talked about Avogadro's number, which is 6.022 times 10 to the 23rd things, whatever we're talking about, the things we're discussing, in 1 mole of those things that we are discussing. Okay, and this grams per mole is whatever chemical you're talking about. Whatever chemical you're talking about. Okay, and these things are going to be chemical. So let's hit that right now. Okay, so when I talk about things in chemistry, I'm talking about atoms. So like you could have sodium, you could have an oxygen atom, you could have a magnesium atom. Okay, I could be talking about ions, and that would be when they have a charge. Right? I'll just use those same ones. Okay, so it's the same thing. It's just when they have a charge, or you could have your polyatomic ions, right? Any of those. Okay, so that's when we're talking about ions. You could have molecules are things, and molecules are typically, we're talking about covalent compounds. Okay, so like if I had CO2 or C6H12O6 or P4O9. I don't even know if that exists, but whatever. A covalent compound. Okay, or ionic compounds, which are, oh, sorry. Let me go the other direction. Formula units, which are your ionic compounds. So like sodium chloride, sodium sulfite, right? Magnesium hydroxide. Okay. So formula units are your ionic compounds. Because remember, when we learned about ionic compounds, like if I had sodium chloride, it comes together in a crystalline structure where all of your negatives are surrounded by all of your positives, right? And that's three-dimensional. That comes out at you and down, back away from you. Okay, it keeps going. And one formula unit of that is that. Okay, so when we say formula units, we're talking about ionic compounds. But some instructors use molecules for both of those and don't use formula units at all. Okay, but just so you understand. So basically, what I want you to recognize here is that these are things. Atoms are not a measurement like grams or milliliters or feet, okay, or meters, okay? Atoms are things. Ions are things. They're not a measurement. Molecules are things. Formula units are things. They are an actual, like, physical thing. It is not a measurement of a thing, okay? So anytime we say, how many of these do you have? We're going to be looking at Avogadro's number because Avogadro's number tells us how many things are in a mole of those things. Okay. Now let's look at how we're going to use this information. Okay, so remember the two things we had really talked about is our number of grams of a chemical and 1 mole of a chemical from our periodic table. And that is your molar mass. The mass of 1 mole. Okay, and we talked about Avogadro's number, which is the 6.022 times 10 to the 23rd. And now I'm going to start calling things particles. Okay, so when I talk about things up here in chemistry, they're really known as particles, right? And an ionic particle, an atom is a particle, a molecule is a particle, a formula unit is a particle. Okay, so for the concept of understanding it, I called them things. Now we're going to call them particles. Okay, so I have that many particles in 1 mole of particles. Okay, so those are the two things that we've talked about. And I might be spelling Avogadro's number wrong. Let me check. Nope, that is correct. The O first, then the A, and then the O again. Okay, so Avogadro's number. Okay, so let's look at how we're going to use these. What if I ask how many grams of, we'll go ahead and use carbon since we had talked about carbon, in 27.0 moles of carbon. Okay, so my question is grams of carbon. And you're going to see I always write my question down. Because if you have a long word problem, you don't want to keep going back and looking at your word problem to see where you need to stop. Okay, I always write my question down. As soon as I see it in my problem, I write my question down. I'm looking for grams of carbon. Okay, well, I've only been given one number, so I have to start with that number. So I'm going to start with 27 moles of carbon. Okay, so remember, when we're going between grams and moles, that's our molar mass off of the periodic table. And if you go to your periodic table, and I'll pop over there real quick, right? And we find carbon, we see that he weighs 12.01. Okay, remember the number at the top is your number of protons and electrons. Okay, the number at the bottom is your mass. Okay, so he weighs 12.01. So using dimensional analysis, which you guys have learned by now, we say that 1 mole of carbon, because it's the mass of 1 mole, is 12.01 grams of carbon. The mole on the bottom to cancel. Those cancel. And I'll do that math real quick, just so we have a number in front of us. Gives me 324.27. Okay, so, excuse me, looking at sig figs, right? We've got 3 sig figs in this number and 4 in that number, so we're going to go with 3 in that number. So I have 324 grams of carbon. Okay, What if I said how many moles of manganese in 97.2 grams of manganese? Okay, so we go to our periodic table. And here's our manganese. Weighs 54.94. So 54.94, this time the grams goes on the bottom in order to cancel grams, and our mole goes on the top. Okay, so 97.2, 4, I get 1.7692 and some other numbers. And we're looking at 3 sig figs here and 4 here. And it's all multiplication division, so we're going to go with the 3. My 9 will round that 6 to a 7, so 1.77 moles of manganese. Okay, what if I said how many grams of manganese 2 phosphate in 3.0 moles? Okay, and since I only mentioned manganese phosphate, then I'm just talking about manganese phosphate. Okay, so we know we have our 3 moles of manganese phosphate. And because we're going between grams and moles, right? Grams and moles, then that means we're going to use the molar mass. So these up here, you only had one thing, right? Or one atom. So we were just looking at the mass on the periodic table. It's just the one thing. Well, now we're going to use the periodic table again, but we have to get the mass of everything that's in that manganese 2 phosphate. Okay? So your easiest way to do it until you get really good at this, and you can just do it on your calculator in one go, okay, is we say, okay, I know I have manganese, I have phosphorus, and I have oxygens. And I have 3 manganese, and manganese weighs 54.94 on your periodic table. I have, right here, I have 2 phosphoruses. And phosphorus weighs 30.97 on your periodic table. And oxygens, I have 8, right? Because if I had 2 of those, I have 8 oxygens. Okay, so I have 8 oxygens, and oxygen weighs 16.00. Okay, so if we do that math, I get 164.82 for the manganese, 61.94 for the phosphorus, and 128.00 for the oxygens. Okay, so on sig figs on that, okay, what we're really doing is we are adding all of those masses together. We're adding them together. And remember, addition subtraction goes by your least number of decimal places. All of these have 2 decimal places. So all of your molar masses on your periodic table, if your periodic table is 2 decimal places like mine is, all of your molar masses will be 2 decimal places because we're adding them. Okay, so now we're going to add all of those together to get our total mass for the whole thing. And I get 354.76. Okay, so that is the molar mass of manganese 2 phosphate. Okay, so we know molar mass is our number of grams in a mole, the mass of a mole. Mole on the bottom in order to cancel. And our molar mass on the top, 354.76 grams. And we're at grams, which is what we're looking for. If I do that math, I get 1064.28. And we have 2 sig figs and 5 sig figs. So we're going to go with 2 sig figs. Okay? But 11 does not mean the same thing as 1064. So you either need to put zeros in to get into your thousands place. Do not put a decimal on the end of that. A decimal on the end of that makes that 4 sig figs. Okay? Or you could put it into scientific notation. Okay, either way you want to do that. And that would be grams of the manganese 2-phosphate. Okay, so let's do another one, but we're going to go the other direction. I'm going to say how many moles of glucose, C6H12O6, in 5.25 grams of glucose. Okay, so I start with the only thing I know, my 5.25 grams of my glucose. Okay, we're going between grams and moles. So again, molar mass. Okay, so if we add those up, carbons, I have 6 of them. He weighs 12.01. Hydrogens, I have 12. Weighs 1.01. And oxygens, I have 6, and they weigh 16. I think that's 72.06. Yep, so 72.06. This is 12.12. And this is 96. Add all of those together. It should be 180.18. That's one mass I actually have memorized. So 180.18. Okay, and that's our grams because the number always goes with your grams, and grams goes on the bottom. So 180.18 grams of my C6H12O6 to 1 mole of my C6H12O6. Grams cancel, we're at moles, that's what we're looking for. And keep in mind, I'm canceling my chemical too, because pretty soon we're going to start talking about 2 different chemicals. Okay, so if I do that math, I get 0.029137 and some other numbers. And I've got 3 sig figs here and 5 here. So I'm going to go with 3 sig figs in my answer. So those 3, so 0.0291, or you could always go into scientific notation and say 2.91 times 10 to the negative 2, right? Because the number's smaller than 1, it's a negative exponent there. If you're curious about that, go back and watch my video on significant figures and scientific notation. Okay? So, and that is moles of C6H12O6. C6H12O6. Okay? So that's going between grams and moles. Okay? Anytime grams is involved, you're going to use molar mass to get to moles. And you're always going to go to moles. If you don't know where to go to moles. Okay, so now let's work with Avogadro's number, and then we're going to mix the two. Okay, so Avogadro's number being the 6.022 times 10 to the 23rd particles. And a mole of those particles. Okay, so what if I say how many molecules C6H12O6 in 4.0 moles? Okay, so my question is molecules. And I'll start with the only number I know, 4 moles of the C6H12O6. Okay. And here is our conversion factor. Mole on the bottom to cancel. 6.022 times 10 to the 23rd molecules, C6H12O6. Okay, and you will notice I did not abbreviate molecules. I spelled the whole word out. Because if you abbreviate that, you're going to attempt to abbreviate it MOL or MOLE. Well, that's moles. Okay, so don't abbreviate molecules, just write the whole thing out. Okay, you're going to be better off that way because then you don't make a mistake. Okay, so if I do that math, I get 2.4088 times 10 to the 24. And I've got 2 sig figs here and 4 here, so I'm going to go with 2 in my answer. So 2.4 times 10 to the 24 molecules, C6H12O6. Okay. Now, what if I said how many moles C6H12O6 in 2.7 times 10 to the 22 molecules? Okay, so now we're going the other way. Our question is moles, and we're starting with the molecules. And you're going to find you're going to run out of room, so you can always like double it, put your chemical up on top. Okay, so we're still going to use Avogadro's number because we're moles and particles, so it's always Avogadro's number. And now we're putting the number on the bottom to cancel molecules. And 1 mole. Okay, our molecules cancel, and we're at moles, which is what we're looking for. Let me do that math real quick. And I get 0.044835 and some numbers. So I've got 2 sig figs here and 4 here. So I'm going to go with 2 sig figs in my answer. So those 2, 8 is going to round that 4 up to a 5. So I have 0.045 moles of C6H12O6. And it doesn't matter what chemical you're talking about. Okay? And you see on those, the molar mass doesn't matter because grams was not talked about at all. So we're not going to use the molar mass on that. We're just using Avogadro's number to get between moles and molecules every single time, no matter what you're talking about. If you're talking about molecules, ions, atoms, formula units, and we want to know moles and those, Avogadro's number every single time. Now I am going to mix those 2 conversion factors. We're going to do a two-step problems. Okay, so remembering that our number of grams in 1 mole is how we get between grams and moles. And 6.022 times 10 to the 23rd particles in 1 mole of particles. Okay, when we're talking about numbers of particles and moles of particles. Okay, so what if I say how many formula units of magnesium chloride are in 55.0 grams? Okay, so I'm looking for formula units, and I'm just going to abbreviate that FU to make it easy on us, of magnesium chloride. Okay, that's our question. And we're going to start with the thing that we know are 55 grams of magnesium chloride. Okay, so I'm actually going to come down here and I'm going to draw us a little map. And there's a reason that I'm going to go vertical on this map instead of horizontal, because in a minute we're going to add something else into here horizontally. Okay, so if I know how many grams of some chemical, I'm going to call it chemical A, that I have, and I want to know how many moles of that chemical I have, I'm always going to use the molar mass of that chemical, right? Off of your periodic table, number of grams in a mole. If I want to know how many particles of that chemical I have, ions, atoms, molecules, formula units, if I want to know that, then I use Avogadro's number every single time. Okay, so on this problem, change my color back. We're going between formula units and grams. So we're starting at grams. That's what we know. We know grams. We're right here. And we want to go to our particles. So first, we have to use molar mass in order to get to our moles. Okay, there is no road to go straight from grams to particles. You have to go through moles to get there. Okay, so first we're going to use the molar mass of magnesium chloride. Oh, I'm going to move this down because I'm going to run out of space over there. Okay, so we were looking between grams and formula units. Okay. Oh, and by the way, I hope I'm not confusing anybody with this. Most people use the lines like this. We call that the railroad track method. Okay, that just means the exact same thing. Let me pop up here. Okay, so if I have this, that means the exact same thing as if I had, or even put parentheses around those. Okay, it's just basically here's my times, and here's my parentheses. Okay, it just saves us from having to draw all of those lines and all those timeses. It just saves time. Okay, so just recognize that we're multiplying the top, dividing the bottom. Okay. Okay, so the first thing we need, again, back to this, we're at grams. We need to get to moles, so we're going to use the molar mass. Okay, so I have 1 magnesium, and magnesium weighs 24.31. And I have 2 chlorides. I know chloride weighs 35.45. Okay, so if I add those together, $95.21. Okay, so our number always goes with our grams. So 95.21 grams of my magnesium chloride in 1 mole. Because remember, our periodic table always tells us grams per mole. Grams cancel. Now I'm at moles. Okay, I want to go to formula units. So now I'm here, but I want to go down to particles. So I'm going to use Avogadro's number to get there. And we know Avogadro's number is 1 mole, and that's on the bottom to cancel, to 6.022 times 10 to the 23rd formula units of magnesium chloride. So moles cancel, and I'm at formula units, which is what I'm looking for. Now I just do that calculation. Oh, no, I did that wrong. And I get 3.4787 and some numbers times 10 to the 23. And we've got 3 sig figs here, 4 here, and 4 here. So we're going to go with 3 in our answer. So 3.4, that 8 rounds the 7 up. 3.48 times 10 to the 23 formula units of magnesium chloride. Okay. What if I said how many grams of sodium hydroxide in 1.70 times 10 to the 27 formula units? Okay. So our question is grams of sodium hydroxide. We're going to start with the one thing that we know. Okay, so looking at our map, let me grab this map real quick. Oh, I did not want to grab that with it, but I got it anyway. Okay. Okay, so on our map here, we are at formula units. Okay. Oh, I forgot to put my sodium hydroxide on there. Okay. So we are at formula units, and we want to go to grams because that's our question, grams. So first, we're going to have to use Avogadro's number to get up to moles. So Avogadro's number is always 1 with the mole. So we know our number goes on the bottom in order to cancel formula units. So it's that many in 1 mole. My formula units, sodium hydroxide, cancel. Now I got to moles, but I want to go to grams. So now in order to do that, I am going to use the molar mass of that chemical. So mole on the bottom to cancel. Okay, sodium weighs 22.99. There's only one of him. One oxygen is 16, and one hydrogen is 1.01, and I happen to know that that weighs exactly 40. Okay, so sodium hydroxide is 40.00 grams in a mole. My moles cancel, and I'm at grams. So now I just do that math. And I get, yeah, that looks about right. I get 112919.2959. Okay, and I have 2 sig figs here, 4 here, and 4 here. So we're going to go with 2 in our answer. Okay, but 11 does not mean the same thing as 112,919. So you either have to put zeros in to get to that decimal place. Don't add the decimal place because then you would have 6 sig figs. Okay, or you could go into scientific notation. Okay, your best bet on this is to go into scientific notation. And the reason is our general rule is 3 zeros or less, you can just use zeros. 4 zeros or more, use scientific notation. Okay, because zeros are really easy to lose when you're writing them down, when you're putting them in your calculator. Zeros are just easy to lose when there's too many of them. So if there's 3 or less, just write them down as zeros. If there's 4 or more, put it into scientific notation. So technically that is how you would want to write that answer. Okay. Okay, so the thing to see here is if we're going between grams and moles, always use the molar mass no matter what. If we're going between moles and particles, which is ions, atoms, formula units, and molecules, between moles and particles, always Avogadro's number, no matter what. Now, what if I am talking about a different chemical? Okay, so let's say that I am talking about chemical B. And I want to know how many moles of B, whatever chemical that is, just like chemical A was just some chemical, chemical B is just some chemical. Well, between grams and moles is always, always, always molar mass. But now you would use the molar mass of that chemical. Okay. So what if I wanted to know how many particles of B I had? Okay. Well, between moles and particles, always, always, always Avogadro's number. Okay. So it's a mirror image. See, it doesn't matter what we're talking about, grams to moles, moles to grams, always molar mass. Moles to particles, particles to moles, always Avogadro's number. Okay. This map is a little cockeyed. Sorry about that. Okay. Now, what if we are talking about two different chemicals? Like, what if I say, how many atoms of oxygen in, oh, not atoms. I'm going to say moles. I'm just going to go start with moles right now. How many moles of oxygen in 42 moles of H2SO4? Okay. So I'm asking about moles of oxygen. That's my question. And starting with the only thing that I have. That's two different chemicals. Oxygen is not the same thing as sulfuric acid. Okay. So I'm talking about two different chemicals. So you have a chemical A and a chemical B. Okay. So how do I get from chemical A to chemical B? Okay. That relationship is the stoichiometry. That's what stoichiometry is. Okay, so remember, stoichio means elements, and metry means measure. And remember, we measure elements by the moles, right? Because they're so small, we have to have them in batches, so we measure them by the moles. Okay, so that's our stoichiometry. I call this my moles of A to my moles of B ratio. Okay. And right now, okay, we're going to move past this in a second and do another thing with this. But right now, you get that information from the subscripts in your formula. Okay, so remember earlier when I was talking about this, I said that 1 mole of H2SO4, sulfuric acid, is 2 moles of hydrogen. That's a conversion factor. 1 mole of sulfuric acid is 1 mole of sulfur. That is a conversion factor, how you get from moles to moles. 1 mole of sulfuric acid is 4 moles of oxygen. Okay? So you don't have to do all of those for this. What we're looking at is we are looking at sulfuric acid and oxygen. Okay, so in 1 mole of sulfuric acid on the bottom, in order to cancel, I have the 4 moles of oxygen. Okay, you just get it from that subscript in your formula. Oh, sorry about that. I was not trying to do that. You just get that from your subscript in your formula. Right? I've got 4 oxygens in 1 of those. 4 moles of oxygen to 1 mole of sulfuric acid. So if we calculate that, I get 168, and we have 3 sig figs here, and oh, these are not used for sig figs. These are absolute numbers. We don't have like 3.9 moles reacting with a mole. They are absolute numbers. Never use your mole relationship, your stoichiometry. Don't use that for sig figs. So we're going to have 3 sig figs, so 168. So I have 168 moles of oxygen in 47 moles of sulfuric acid. Okay, what if I said, okay, so let's add on a little bit here. What if I said how many grams of oxygen in 25 moles of H2SO4? Okay, so our question is grams of oxygen. We're starting with that 25 moles H2SO4. Okay, so again, we have two different chemicals. Oxygen's not the same as sulfuric acid. So we come up here and we are at, oh, let me look here. So we're at moles of sulfuric acid. So we're at moles of a chemical. And we want to know grams of the other chemical. So we need to go to moles and then up to grams. Okay. So we're going to use the subscripts in our formula, and we're going to use the molar mass of the second chemical. Okay. And just so you see, it doesn't matter which one you call A and which one you call B. You're starting with the one that you know the number. So if you said, okay, I called my sulfuric acid B. Okay, so my starting place, if I called that B instead, we're doing the same thing. We're still going to use the stoichiometry and the molar mass. Okay, so it does not matter which one you call A and which one you call B. You just follow your map. Okay, so our first step, we're at moles of one chemical. We first need to go to moles of the other chemical using the subscripts in our formula. Okay, and in one of our entire compound, 1 mole of our entire compound, how many moles of the oxygen do I have? Well, that's my subscript. I have 4. Okay. So we got to moles of oxygen. So we just went from our moles to our moles using our stoichiometry. Now we're looking for grams. So now we're going to go from moles to grams using our molar mass. Okay, so we know molar mass is off the periodic table. So 1 mole is the mass of 1 mole. And on your periodic table, oxygen weighs 16. Our moles cancel, and we're at grams, which is what we're looking for. And I get 400. Excuse me, and I've got 3 sig figs here and 4 here, so we're going to go with 3. So all 3 of those are significant. So we cannot leave it as just 400. We have to put a decimal behind that to force it to be 3 sig figs. Excuse me. Remember, your zeros, ending zeros, are significant if there is a decimal anywhere in the number. So we have to put a decimal in that number in order for it to have 3 sig figs. So there's 400 grams of oxygen. Okay, what if I said how many grams of nitrogen in 37.0 grams of magnesium nitrite? Oh no, I'm going to make this aluminum nitrate just because. So aluminum nitrate. Aluminum's +3, nitrate's -1. So I need 3 nitrites on there. Okay, so our question is grams of grams of nitrogen. And we're going to start with, guess I don't need to write that down, grams of nitrogen. We're going to start with the only thing we know are 37 grams of aluminum nitrite. Okay. So I am at grams and grams. Okay. So let me grab my map. I'm going to loop that guy, bring him down here so we can see. Okay. So I am at grams of one chemical, and I want to know grams of the other chemical, grams to grams. So first I'm going to use the molar mass of my first chemical. Then I'm going to use my stoichiometry, and then I'm going to use my molar mass of my second chemical. Okay. So first, we need the molar mass of aluminum nitrite. So aluminum, I have 1, and aluminum weighs 26.98. Oh, I'm going to run out of space. Let me move this over. So aluminum, I have 1 aluminum at 26.98. Okay, and so nitrogens, I have 3 nitrogens at 14.01. And oxygens, I have 6 oxygens. Okay, right? Because if I had 3 of these, I have 6 oxygens. Okay, so 6 oxygens at 16 each. Okay, calculating all that out. And I get 185.01. Okay. All right. So let me just double check that. Something seems weird about that. So 96, 203, 46.98. Oh, that's why I put in the wrong number. 26.98. I knew something felt weird about that number. That is 165.01. Okay, so we know molar mass is our number of grams, and grams on the bottom to cancel. So that many grams of the aluminum nitrite to 1 mole, because molar mass is always the number of grams in 1 mole. Grams cancel. Now I'm at moles. So I just went from my grams to my moles. So now I need to go from my moles to my moles. Okay, so let me talk about this for a second. I always look at this as like, this is a river. This is my mole river coming down the middle here. Okay, that's my mole river flowing down the middle there. Okay, over here is one bank of the river, and over here is the other bank of the river. And if you're talking about 2 different chemicals, you got to cross the mole river. You got to get across that mole river. Okay, and I call this my mole bridge. I have to take the mole bridge to cross that. That's my stoichiometry, is the mole bridge, because that is the spot that you will forget. It is the spot every student forgets. It's the spot every student struggles with. If you struggle with something, that is probably what you're struggling with, is the stoichiometry. So when I look up here and I see I have 2 different chemicals, I have nitrogen and aluminum nitrite, I get in my head automatically, I absolutely am going to have to cross that mole river. And you cross the mole river as soon as you get to moles. Once you're at moles, that's where you cross the mole river. Okay, so remember, in one of my big chemical, one of my entire compound, 1 mole of that, how many moles of nitrogen do I have? I've got my 3 moles of nitrogen. Moles of aluminum nitrite cancel. Okay, so I went first from grams to moles using my molar mass of aluminum nitrite. Then I went from moles to moles using my stoichiometry. And now I'm going to go from moles to grams using the molar mass of that chemical. Okay, so we know mole on the bottom to cancel, and molar mass is 1 mole, and nitrogen weighs 14.01. And we are at grams, which is what we're looking for. Now we just do that calculation. So, and I get 9.4192 and some other numbers. And here I have 3 sig figs, 4 sig figs, and 5 sig figs. So I'm going to go with 3. That 9 is going to round the 1 up. So I have 9.42 grams of nitrogen. Okay. So it's what I want you to recognize is anytime we're talking about two different chemicals, you're going to have a mole over mole. Okay, a mole to mole relationship, a mole to mole conversion factor. We're talking about two different chemicals. I have a mole to mole conversion factor. Okay, and you always just look at where you're starting. This one started with moles, so we started at moles and went this way. Okay, this one started at grams. So we started at grams instead of moles and went this way. We had one more conversion factor on there. Okay, so I'm going to do one more. What if I say, how many atoms of oxygen in 25.0 grams of water? Oh, no, I don't want to use water. Let's use, hydrogen peroxide. Let's use H2O2. Okay. So my question is atoms. I'm going to start with the thing that I know. Okay, so again, two different chemicals. We're going to have to cross that mole river. Okay, got to cross the mole river. So first we have to get to moles. Okay, so remember, I've said a few times, if you don't know what to do, go to moles, because moles takes you everywhere. Okay, so first we need the molar mass, because we're at grams. So first we're going to use the molar mass. Oh, let's look at what we're looking at here. So we're going to atoms of one from grams of the other. So we're at grams, and we're going to particles. So we're going to use molar mass, stoichiometry, Avogadro's number. Okay, so first the molar mass of two hydrogens. Oop, no space there, and two oxygens. Okay, so I'm 34.02. So hydrogen peroxide weighs 34.02 grams in 1 mole. And remember earlier when I was saying our chemical cancels too, and that's important? Now is why it's important, is because when we're at this mole to mole ratio, you need to know which chemical you're canceling, where you're coming from, and where you're going. Okay, so we just went from grams to moles using the molar mass of hydrogen peroxide. So now we're going to cross that mole river using our stoichiometry. So in one of my entire compound, 1 mole of that, how many moles of oxygen do I have? I have 2. The subscript's in your formula. So 2 moles of oxygen. Okay, so I just went from grams to moles to moles. Now I'm going to particles using Avogadro's number. And we know Avogadro's number is 1 mole, and that's on the bottom to cancel, to 6.022 times 10 to the 23 atoms of oxygen. And that's what we're looking for. Now we just do the calculation. I get 8.85067 and some numbers times 10 to the 23. And I have 3 sig figs here, 4 here, and 4 here. So I'm going to go with 3 sig figs, those 3. So 8.85 times 10 to the 23. That's atoms of oxygen. Okay. So we are just following that map. Okay. We're gonna move on now in a second, because remember I told you for now we're using our subscripts. So in just a minute, I'm going to move to a balanced equation, right? Because we learned how to do balanced equations. So now we're going to start using balanced equations for that stoichiometry. But the thing I want to point out to you is when you get to an exam or a quiz, recognize that my lines here are an H. Okay, so I have an H. Oh, I guess I need some color there. I have an H. Okay, but kind of broken up, but it's an H. We know grams goes on the top, moles in the middle, because moles is your hub. Moles takes you everywhere, so moles has to be in the middle. And then your particles on the bottom. Okay, we know that our grams to moles is always our molar mass. We know moles to particles is always Avogadro's number. And moles to moles is your stoichiometry. So you could just draw yourself a quick little cheat sheet on your scratch paper before you start your quiz or exam, and then just follow your map. Okay, if you know grams of one chemical and you want to know particles of the other, you know that you're going to use a molar mass, stoichiometry, Avogadro's number. If you were starting with particles of one thing and you wanted to know particles of the other, you would use Avogadro's number, stoichiometry, and Avogadro's number again. Okay, no matter what. And if you're talking about only one chemical, you're not crossing the Mole River. You're staying on one side of the river because you're not talking about two chemicals. Okay, so you can just draw yourself a little cheat map before you start your quiz or your exam, and then you just follow your map. Okay, now I'm going to talk about if we're doing this with chemicals in a balanced equation. Like so far, I've done this with just a single chemical, just one, well, two chemicals, but a compound, and we're looking for something that is within that compound. Those are my two different chemicals. Now we're going to do it with a balanced equation. Okay, so let's say that I have, let me get some color here. I have magnesium sulfate reacts with sodium phosphate. So remember balancing equations to make sure our formula is true. He's a +1 -3. So I need 3 sodiums. Okay, a double replacement reaction. So my magnesium hooks up with my phosphate and sodium hooks up with my sulfate. So magnesium hooks up with phosphate. Sodium hooks up with sulfate. Okay, magnesium's +2, phosphate's -3, so I need 3 magnesiums, 2 phosphates. Sodium's a +1 and sulfate's a -2, so I need 2 sodiums, 1 sulfate. Okay. Okay, so we got our products based on our type of reaction. It's a double replacement reaction. We made sure our formulas are correct. I'm going to put the states in. Magnesium sulfate, oh, I do not remember. Yes, magnesium sulfate is soluble. And if you're struggling with solubility rules or you haven't learned those yet, if you haven't learned those yet, don't worry about it. If you're struggling with them, go back and watch my video on solubility rules and how to use your solubility rules. So this is aqueous. It dissolves in water. It is soluble. Group 1 metals, sodium, always soluble. Group 1 metals, always soluble. And phosphates are insoluble except with rule number 1. So this is a solid. Okay. And if I say how many formula units of sodium phosphate are required to produce, oh, yeah, I'll say produce, to produce 50 grams of sodium sulfate. Okay. So our question, I always have my question here. So our question is formula units of sodium phosphate. We'll start with the only thing we know, 50 grams of sodium sulfate. Okay, so I'm just going to go up to our little map that we had up here. So I am starting at grams, and I'm going to formula units of a different chemical. So I'm starting at grams. I'm going to formula units of a different chemical. So first I'm going to use the molar mass of my first chemical, my stoichiometry, and Avogadro's number. Okay? But that stoichiometry now crossing the mole river, okay? I can't get it from my formula because there isn't sodium phosphate in the formula of sodium sulfate. Okay, it's not within that formula. So I have to get it from another place. And this is where I get it from. I get it from my balanced equation. Change my color there. Okay, so now this comes from the balanced equation, your coefficients in your balanced equation. The big numbers in the front, coefficients in your balanced equation. That's where you get the information from. If you have a balanced equation, that is where you get your information from. If you do not have a balanced equation, it comes from the subscripts in your formula. Okay, so we have an equation, but I have not balanced it yet. So let's balance this real quick. Okay, so remember, I always like to start with the one that has the most stuff, and I think that's magnesium phosphate here. So I have the 3 magnesiums, right? I have 3 magnesiums there and 1 here. So I'm going to put a 3 in front of my magnesium sulfate. I have 2 phosphates here, and I have 1 over here. So I'm going to put a 2 in front of my sodium phosphate. Remember, since I started over here, I'm going to finish over here. Stay very organized about this. So I have 2 sodiums here and 6 sodiums here. So I'm going to put a 3 in front of my sodium sulfate to give me 6 sodiums. And that gave me 3 sulfates. And I have 3 sulfates. Okay, so now we have a balanced equation. Okay, so I'm starting at grams. So the first thing I need to do is go to moles, because we always go to moles first. It's where we always go. We always go to moles no matter what. Okay, so grams to moles is the molar mass. So now the molar mass of that, I have 2 sodiums at 22.99, 1 sulfur at 32.06, and 4 oxygens at 16 each. We have 45.98. This is 32.06. I guess 64. Okay, so if I add all those together, I get 42.04. Okay, so remember our molar mass, because that's what we're using right now, is our molar mass. Molar mass is always 1 mole. That'll go on the top because we're canceling grams. And I have 142.04 grams of that sodium sulfate and a mole of sodium sulfate. Okay. So I just went from grams to moles using molar mass. So now I have to cross that mole river because I'm talking about 2 different chemicals. So I'm going to cross the mole river using my coefficients in my balanced equation. So we know that we want sodium sulfate on the bottom to cancel. And our other chemical, this is why I always write my question down so I don't have to go back and read my problem, sodium phosphate on the top. Okay, so we go to our balanced equation, and I have 2 sodium phosphates for every 3 sodium sulfates. So 2 moles of sodium phosphate to, 3 moles of sodium sulfate. Okay, we just use the coefficients in the front because we may be used to say that 3 formula units of this reacts with 2 formula units of this, right? Now we're saying moles. Okay, so 2 moles of sodium phosphate to 3 moles of sodium sulfate. My moles of sodium sulfate cancel. And I'm looking for formula units. So I just went from grams to moles, moles to moles. Now I'm going to use Avogadro's number to get to my formula units. And we know Avogadro's number is 1 on the mole, and that's on the bottom to cancel, to 6.022 times 10 to the 23rd formula units of that sodium phosphate. Moles cancel. I'm at formula units, which is what I'm looking for. Now I just do the calculation. It's 50. So I get, put it down here, 1.4132 and some other numbers times 10 to the 23. And here I have 3 sig figs, 5, and over here is 4. So I'm going to go with 3 sig figs, those 3 right there. So 1.41 times 10 to the 23 formula units of sodium phosphate. Okay, just following my math. We'll do one more with a balanced equation, and then I think we're going to call it a day after that. Okay, so what if I have sulfuric acid or sulfurous? Let's go with sulfurous acid just for fun. Reacting with sodium hydroxide. Okay, and no, let's react that with magnesium hydroxide just for fun. Okay, so double replacement reaction. H hooks up with OH, magnesium hooks up with phosphate. So my magnesium hooks up with my phosphate, my H hooks up with my OH. Remember, if you watched my balancing equations video, acid plus a base, acids with hydrogens in the front, bases with OHs in the back. Okay, they always make water, and it's easier to balance if you see water as HOH. So let's make sure our formulas are true. I have a +2 and a -3 on the magnesium phosphate. So I need 3 magnesiums, 2 phosphates. And we know water is water. And I gave these over here to you, so those are correct. Okay, so now if we go to balance this thing, I'm going to start with magnesium phosphate because he's got the most stuff in him. So I have 3 magnesiums here and 1 here. So I will put a 3 in front of the magnesium hydroxide. I have 2 phosphates here and 1, oh, that should be phosphite. Sorry, you probably noticed that. That's a phosphite. Okay, I have 2 here and 1 here. So I need to put a 2 in front of my phosphorus acid. Remember, I started over here, so I'm going to finish over here. I have 1 hydrogen here and 6 hydrogens from my acid. So I'll put a 6 in front of water, and that gave me 6 hydroxides, and I have 6 hydroxides. So I'm balanced. So what if I say, how many molecules of water? I just made this really hard on myself, but that's okay. Of water are produced when, no, maybe I didn't make it hard on myself. When 4.39 times 10 to the 27 formula units of magnesium phosphate are also produced. Okay. And the main reason I wanted to do this is because I want to show you, well, let's write it down first. So I'm looking for molecules of water. That's my question. And I'm starting with the only number I have, 10 to the 27. Okay, move that a little bit so we can see what we're doing here. So how many molecules of water is our question? And we're starting with formula units of magnesium phosphate. Okay, so two different chemicals. So we know we're going to have to cross the Mull River. No matter what, you're going to have to cross the Mull River. Okay, so I am at formula units of one chemical, and I'm going to molecules of the other chemical. So I'm going to use Avogadro's number. I'm going to cross the Mull River using my stoichiometry, and I'm going to use Avogadro's number again. Okay, so we know Avogadro's number is 1 on the mole, and that's going to go on top because I need to cancel the number on the bottom. The 6.022 times 10 to the 23rd formula units. Okay, the formula units has to go on the bottom, so the mole on the top. So my formula units cancel. Now I'm at moles. Okay, so I just went from formula units to moles. Now I'm going to cross that Mull River using my balanced equation. Okay, so I have to cross the Mull River. So we know that we want magnesium phosphate on the bottom to cancel. And our other chemical on the top, which is water. So we know we want water on the top. Okay, and this is why I wanted to do it this way. As you see, these are both products. Okay, you can compare any two chemicals in a balanced equation, any two things. They can both be products. They could both be reactants. I could have one product and one reactant. I could have one reactant and the other product. I could have any two chemicals in a balanced equation can be used in stoichiometry. They don't have to be one product and one reactant, okay? It can be any two chemicals. Okay, so in our balanced equation, our moles of water, we have 6. And our moles of magnesium phosphate, oh, I keep putting phosphate. Let me fix that. This is phosphite. Phosphite. Okay, so I have 1 mole of magnesium phosphate. My moles of magnesium phosphate cancel. Now I'm at moles of water, and we're looking for molecules. So we just went from formula units to moles using Avogadro's number. We used our stoichiometry to get to moles. Now we're going to use Avogadro's number again to get down to our molecules. Okay, so we know Avogadro's number is 1 with the mole, and that's on the bottom to cancel. 6.022 times 10 to the 23rd molecules of water on the top. And we are at molecules of water, which is what we're looking for. Now we just do the calculation. Okay. What's kind of nice in this, if you catch it, is if we're going from particles to particles and using Avogadro's number twice, technically, those just cancel out, right? I can cancel those out and I don't even need to put those in my calculator because one's on the top and one's on the bottom. Okay, if you feel more comfortable putting it in your calculator, then put them in your calculator. But if you have one on the top and one on the bottom, they cancel each other and you don't have to bother putting it in your calculator. Okay, so if I calculate this, I get 2.634 times 10 to the 28. And here I've got 3 sig figs, 4, 4. So I'm going to use 3 sig figs, those 3 right there. 2.63 times 10 to the 28 molecules of water. Okay. Okay, so that is stoichiometry. Okay, that is just, you are just going from grams to moles to particles to, okay, but no matter what, if you don't know what else to do, go to moles because you can get anywhere from moles. Okay, so that is stoichiometry, and it's this step right here. It's that mole ratio. It's the stoichiometry crossing that Mull River. that most students are going to struggle with. Most students forget that step or get lost when they go to do that step. Okay, so I'm going to show you a sheet that I have, one that I've made that's a little bit neater and prettier. Okay, so here's my sheet, right? To get from grams to moles, molar mass. I don't have a highlighter on this one. I guess I'm just going to have to do this, right? To get from grams to moles, always using your molar mass, which is your number of grams per mole. Same over here, to get from grams to moles, molar mass, number of grams per mole. To get from moles to particles, always Avogadro's number. Moles to particles, always Avogadro's number. And then here, to get from moles to moles, to cross that mole river, if you have a balanced equation, which you most often will in the future, you're going to use the coefficients from your balanced equation. If you do not have a balanced equation, you're going to use the subscripts in your formula. Okay, so that is stoichiometry. And remember, you can just draw yourself a quick little map when you get into your test, right? It's an H, grams on top, moles in the middle. Things or particles. I'll stick with particles. I'm being a little bit sloppy because you'll just do this real quick before your exam. You know that this is molar mass. Molar mass. You know that this is AVO. This is AVO. And you know that that is your stoichiometry. Okay? Okay, so that is stoichiometry. And later on, when we get a little bit further in the class, you're going to have another road that comes into moles from liters. Okay, we're going to have two more roads on here that come from liters. Liters of A and liters of B, both leading into moles. Okay, and that's going to be pretty much the final road on our map when we get to that. Okay, and so like I said, that's going to go to moles from liters. So no matter what, go to moles. If you don't know what else to do, always go to moles. To get there from grams is molar mass. To get there from particles is Avogadro's number. All right, so yeah, that is all I have to say about that today. Have a great day.